You see my screen?
Yes.
So, now I will discuss about 3.1 and 6 until 3.1 and 8. This talk about low temperature specific heat of copper and platinum. Oh, sorry. So the specific heat of copper is increased at low temperature. In this, so the copper is a very important material, mostly used for low temperature equipment because it has anomaly in specific heat. So the specific heat of copper is enhanced at a low temperature, and this is caused by at this range of temperature at 0.03 Kelvin until 2 Kelvin. The increasing of specific heat at low temperature caused by hydrogen or oxygen impurities, magnetic impurities such as iron and manganese, and also lattice effect. And at the millikelvin temperature, this anomaly also happen caused by nuclear quadruple type contribution. I don't really know about this actually, but this book is referred to the chapter 10 to this equation about the nuclear quadruple specific heat. Uh,
Yeah,
and
basically similar to the magnetic specific heat, right? The
yes,
Schottky anomaly. So
this, uh,
quadruple interaction makes some split energy states
yes,
or the free spin, I mean impurity spin that makes low temperature Schottky like specific heat.
okay, yeah, this related to the magnetic specific heat, nuclear magnetic specific heat at low temperature. And so because these anomalies of specific heat of copper, there are many applications of copper in such in calorimetry, in thermometry. It will be discussed more in chapter 12, and also the nuclear magnetic cooling in chapter 10. And from this graph, show the heat capacity of 275 mole of copper, which 104 mole are in given magnetic field. So we see these full lines are the nuclear magnetic heat capacities with plus electronic contribution to the heat capacities of all mole copper. It means 275 mole. Gathered from the theory, and the deviation measured data is caused by I is equal to 3/2 nuclear levels because of this electric quadruple interaction. And by the proper heat treatment from copper, so it maybe could remove some these anomalies, uh, increase of specific heats. And next is platinum. So platinum, low temperature properties of platinum is influenced by small concentration of magnetic impurities. For example, uh, these books refer to this paper. They investigated two platinum samples containing 11 and 41 ppm magnetic impurities of iron. So we see this is the experimental setup of yeah, this the kind of calorimeter, experimental setup for platinum calorimeter, and they gathered this data, the heat capacity of platinum with impurities of iron, and with at 1 millikelvin and 11 millitesla field, The specific heat is increased. We see from this graph the result of this experiment. Yeah.
Mm.
And,
Oh, yeah. So peak position, do you know what the peak position corresponds?
position.
In the figure, the Schottky's heat capacity peak is changing by applying magnetic field.
Yes. Mm.
Do you know what that coming from? And height.
It's it in this paper tells about the giant's moments, like because
Yeah, iron moment. Yes.
really, yeah.
But basically, that this is coming from same with equation 3.19. Right? This is magnetic Schottky specific heat.
3.19.
So basically, the temperature corresponds to delta E, which is gap between the lowest state and the highest state. And if you apply field, this delta will increase, right? Because of Zeeman splitting. That's why temperature is shifting. So magnetic Schottky specific heat is, if you apply field, the Zeeman splitting happen, then gap increase, the temperature will move. That's why if you apply higher magnetic field, you will see this effect at higher temperature range.
Yes.
And the peak height is basically coming from the what kind of spin you have. Basically degree of freedom, spin degree of freedom. So it was I don't remember, maybe Angelina was talking about this or Black talking about this. I forgot, but the last session section was talking about this.
Okay. And this is the data of specific heats of several materials. If you want to do detail of data, we can see from the textbook. And next is about the calorimetry and how to measure heat capacities. So to measure heat capacities, we have to refrigerate the materials with the mass M to the starting temperature Ti, yes, it's called it. And then we isolate them from the environment. For example, by opening heat switch, and heat switch will discuss in the next chapter, maybe later. Then supply some amount of heat to reach the final temperature Tf. So this is the image, simple image of calorimeter, or the calorimeter consists of a platform with sample, thermometer, and heater are connected. And the problem of the heat capacity measurement is about the low accuracy. So the next is about the important things that should be considered to achieve high accuracy calorimetry. In the adiabatic heat pulse method, this will tell about this method. So the first things that important that the heat switch is necessary to connect or disconnect calorimeter to a bed, and the heat capacity of other object in the system should be lower compared to the sample, or using the heat capacity of the known container. So, or we if we have known heat capacity of the container, the without the sample, so we can subtract from the total value to get the real heat capacity of the sample. And the next is the leads to the thermometer and heater must have low thermal conductivity. For example, using thin superconducting wires. And thermometer, the heater and sample should be well thermally coupled to the platform. Yes, because it should be same temperature. And the power needed to read thermometer should be small to reduce the heat because of the power on the measurement. And the next is one thing that should be considered is using the thermal shield with the temperature close to the temperature of the calorimeter. So and also the heat produced by opening or closing heat switch, it should be small so that it doesn't affect the measurement. And when exchange gas is used for cooling down the calorimeter, so this gas should be pumped away before we do the measurement. Then this is usually quite time consuming, so there will be like absorption or desorption reaction in the inside the calorimeter, and so make the residual gas. So it could be heat produced. So we should consider about this also. And the last is about calibrated and sensitive and stable thermometer is needed for high accuracy. And so the accuracy of heat capacity data usually around 3 to 5%, rarely better than 1%. So if high accuracy is needed or if the parameter of the setup are not well known, so the quality of so if we want to check the quality of calorimeter, we should have to measuring the heat capacity of well-known reference sample, such as high purity copper, yeah, to make the comparison. And okay, and this is one of the ones of adiabatic Hill pulse calorimetry with respect to the temperature resolution. So in this papers, they measure the specific heat of liquid helium in zero gravity, very near the lambda point. So this is like an extreme experiment because they measure the specific heat of liquid helium near the spoke transition uh, the in the other flight. So they measure on the orbit, yeah, to reduce the gravitational effect, and because this will influence the pressure, will make the pressure gradients. So the pressure will affect the temperature over the liquid sample on the different heights. So they measure on the flight, on the orbit. And then they also using for thermal control stage in series with calorimeter. So the last one of control stage has the stability less than 0.1 nanokelvin per hour. Yes, and also using the magnetic shielding, and they also use what is it? Yeah. So we use a high resolution magnetic susceptibility thermometer to measure. so they can get the resolution in sub-nano Kelvin. Yeah, and this is important to yeah, to investigating the phase transition of liquid helium. So the phase transition shows we see the required sharpness from this. If maybe if you want to detail what kind of experiment, you can read this journal. Yes. Okay. That's all for me, but I still didn't explain about the next part is nuclear magnetic heat capacity. Maybe next week.
Nuclear heat capacity. Okay. Okay. Well, okay. What? How up to where you have to present? I mean, this section is really long, right? 3.2, yeah. See, it's all about the thermometry method. I mean, heat capacity measurement method, right? 3.18 is will up to page 85, 58.
Yes. Yes.
But that's too long to me for one person. Anyway, yeah. Do you have any? Maybe people can you can ask a question to her. Any question? If nobody asks, I will ask. 'Do you understand everything? Why you use superconductor, a superconducting wire? Yeah, please show me the slide. Maybe it's better to. Okay. Maybe the one before, maybe. Maybe the fifth one, maybe. You're talking about superconducting wires. Yeah, I asked this question in this afternoon to Japanese students, actually. Superconducting is, zero resistivity, so sounds like everything will go through. Why you want to use that for the low thermal conducting as a low thermal conducting wires? And what carry heat for the metal wires normally?
Maybe because of the heat.
Yeah, heat will be propagated because of what? I mean, what is the carrier for the heat?
Because we have the resistivity of the wires and the heat will extern the losses of power.
Yeah, resistance is show up because of the scattering of the electron will scatter with a phonon or like a internal lattice defect or impurity, right? And basically, the heat will be carried by the electrons, conduction electrons. And normally metal have a many conduction electrons. That's why metal is very good thermal conductors. What about superconductor? Do they have a conduction electron?
The Cooper pairs.
Yeah, they are basically conduction electron forms Cooper pair, and the normal conduction electron disappear. Right. That's why I mean there's no conduction electron which can carry the heat inside the superconducting state. And if you want to make that heat carrier, you have to break a superconducting state and break up the Cooper pair into the conduction electrons. That's why superconducting state is very well, very bad heat conductors. So that's why people use superconducting wire or superconducting material to make a heat switch or adiabatic space. Yeah. That's why they use superconducting wire for the heat capacity sample platform. And yeah, maybe you can easily imagine by showing some picture. I can show you some picture, which is actually the measurement of the Makino-kun last week. So this is a heat capacity cell. And this heat capacity cell includes the thermometer. Now its sample is here. Sample is at the center. And the top part is the thermometer reads, and the lower part is heater reads. And the heater and thermometer is behind this plate, small plate in the center. And basically, this platform is hung by the 4 wires. And it just connect to the heat bus with only 4 wires. So small heat will come in, and small heat can cause out. So this is not the completely adiabatics measurement technique. So heat capacity measurement there are several heat capacity measurement technique. And most easiest one is to understand the method. Most easiest one is basically adiabatic method. In there, you have to make a completely adiabatic space for instance, by using superconducting wires. And this picture is about the relaxation method. In there, you have a weak link between the heat bus to the sample plate, but not completely adiabatic. And adiabatic method, you will measure the heat capacity by adding energy to the heat capacity cell, this platform, including sample, and see the temperature rise. Then dQ over dt will give you the heat capacity. But the relaxation method, you have to measure the relaxation time of the temperature. You have to add some heat and decrease the turn off the heater and see the relaxation of the temperature of the the platform, including sample. Then you can calculate heat capacity. And the third one is AC method, which in that case, the heat bus and the platform is even strongly connected. And you have to give the AC signal, AC current to the heater. Then the thermometer will react the AC, the same frequency. Then you can detect the heat capacity. But of course, to get the absolute value of heat capacity is really difficult with this method. So, but easier to cool down. So each method have an advantage and disadvantage. and understand all of them is important if you want to do the seat capacity measurement. If you want to do, I got the PhD with heat capacity measurement. That's what I know. But if you don't intuit the heat capacity measurement, don't maybe you just have to know the knowledge. It's okay. Okay. I just wanted to share this picture and some explanation. Any question to Erlina? Or you can ask me question too. Okay. If not the case, maybe we can finish today's book reading.
Thank you for attending this book reading.
Okay. So have a nice weekend. Bye.
Goodbye.
Bye.
Goodbye.
Bye.